Hello, everybody. Let us start our discussion today. We have talked about local inertial frames and we evoked the idea of manifolds, particularly differentiable metric manifolds or differentiable manifolds where a metric is defined. And these manifolds, such manifolds, will serve for us the purpose of a local inertial frames. The structure of the local inertial frames will be described mathematically by such a manifold. And we said local inertial because we understood from the principle of equivalence that such a manifold, if you look at smaller region or neighborhood of any event, so at neighborhood of any event, the manifold is Minkowskian, or that is the locally that is inertial. And accordingly, in general, though we have a metric, say g alpha beta, which is a function of the position, however, when we go to the local inertial case, which is that we are looking at g alpha beta in the neighborhood of a point, this is eta alpha beta, which is the Minkowski metric. Remember that eta alpha beta is nothing but diagonal of 1 minus 1 minus 1 minus 1. That is how we have defined it. So this is what we said is the property of a differentiable manifold, the property of the metric in a differentiable manifold where it is defined. And what we will try to do today is we'll try to justify this. We'll ask the question, can we always find a coordinate transformation from an arbitrary coordinate system to a local inertial coordinate system where I can find that my metric becomes eta alpha beta. Now, as we have already seen that there are curvilinear coordinates, and even if I consider the Euclidean uh, space, and I can have, say, for example, 2D polar coordinate where the metric does not quite look like one diagonal in case of the Euclidean space. But that is not the point. The point is that I should always be able to find out a coordinate system where it is possible. We are not saying that all coordinate system in which the metric will look like eta alpha beta. Okay, so let us try to see what exactly that the statement is, the statement that we are trying to make here, and we'll try to proceed in kind of proving the statement. So let's assume we have a manifold M, and here when we are talking about special relativity or general relativity, whenever we talk about a manifold, it is D equals to 4 dimensionals, one of which is time-like and the other three are space-like. And this manifold has a metric G. Metric is a tensor, so I write it this way. So this is my presumptions. This is the assumption with which I am starting. This is the background in which we will work. This exists. Now, what is that we are trying to do? We said that, okay, so let me kind of make a cartoon of the manifold here. This doesn't mean anything. It just let me draw M in whatever way, in an arbitrary way, and say with respect to some origin and some coordinate system, I have a point here P and the point P has the coordinates, say, you can wish whatever it is, so it says x alpha. Okay. So x alpha is the coordinate of the point P, and as you can see that O, which is the origin of the coordinate system in which I am writing these coordinates, is quite far away from P. So it's not local to P. Now what I do is that I try to figure out if there exists a coordinate transformation which let me write as lambda alpha beta prime. What does it supposed to do? So say I have the same manifold, but now I choose the coordinate, choose the origin very next to P. So it's a local origin, and with respect to that local origin, I try to write down the coordinate of P or all the other points near to the P. The coordinate of P in this case is, or any point near to the space, is case is, say, the coordinates are this. Coordinate of P can be, you can consider it to be x beta prime. The question is, can I have a set of transformations such that here the metric, if I want to write, the metric here will be g alpha beta, which is a function of the position x, but here it will be just eta, say, mu prime. And that's eta, that's diagonal 1, minus 1, minus 1, minus 1, not a function of the coordinates. So is that possible? Or more precisely, what you really want is to write the metric here as eta, and it will be locally true with eta, but should not be true with eta when you go further away. So this we claim that this will be off by the square of the coordinates instead of the linear of the coordinates, which also means that del g mu prime say alpha prime is 0 at P. So if I calculate this derivative at P, only at that point, then locally this derivative is 0. So we are asking the question, can we figure out such a transformation matrix lambda alpha beta prime? And let me remind you that lambda alpha beta prime by definition is, this is a short form for del x alpha del x beta prime. This is all that we are asking right now. Can I find such lambda alpha beta prime? So the transformation is not known. We are asking the question, can I find such a transformation such that this holds true? If I can find such a transformation, if I can show that I find such a transformation, then the manifolds, the differentiable metric manifolds, serve as our manifolds for doing general relativity, because as we have seen that general relativity, the coordinates are locally inertial, and that inertial coordinate system is a metric of eta, and that will be satisfied if this is satisfied. Now, one thing one should note here, that the kind of transformation lambda alpha beta prime we are talking about here is not a coordinate transformation of the kind like you go from Cartesian to polar. It is not something like that. It's more deep. What it is, we'll come back to again later, but it's not quite like a simple coordinate transformation. So a simple coordinate transformation is different than what you are looking at here. Now, how do I see if this is happening? So the transformation, let's first write down the transformation. The transformation is that, so G, this is G in the local system, local, so this side is local, near to P. This should be given by G alpha beta. This is non-local. So G alpha beta is the G from this arbitrary system, which is certainly non-local. And you know that how to do the transformation. So these are G's are tensors. So it should be this. And you are trying to figure out that if such lambda exists. Okay. So now, before we go any further, let us say that the P has the coordinates in the local system as the coordinates say x naught gamma prime. So this is the coordinate of the P as seen from the local coordinate system. So it's not necessary that you choose the origin at P. You can do that and do the entire calculation. There is no harm. But we have kept it a little more general. We said that it's not at the origin is not at P, but very near to P. So that is x0 gamma prime. So the local systems you are writing as primes. Now this, the left hand side, I can write as then g mu prime nu prime. This is supposed to be a function of the coordinates of the local system, but I can do a Taylor expansion about P. So the value of g mu prime nu prime at P, and then you add the first, say, let's add the first two Taylor terms. So this is the difference of the point where I want to calculate G from P, and then you need del G plus half. Here I will need square of this difference in the coordinate. Now, as you know by now, that I should choose a different index, which I chose to be lambda prime here, and this I can now write as gamma prime lambda prime. So there are two derivatives. I just have written that way, and plus higher order terms. Right? This is what I want. So we'll call these by different names. So this is what we'll call the zeroth order, just because it has x minus x naught to the power 0. This I will call first order. I mean, the entire term, I'm just highlighting why I'm calling this. That's why I'm making box around those parts. So it's the first, second order terms, etc. Okay. So this is all the left hand side, that is, of this equation g mu prime nu prime. Let us try to see what the right hand side is. Okay. Now to see what the right hand side is, I have to first let's look at g alpha beta first. So we can Taylor expand g alpha beta around P. The exact same thing that I have done with the left hand side. So what will that be? So g alpha beta Remember that this is, just to remind you, this is a function of the position and this is the global g alpha beta. So g alpha beta, this will be, first you have to write it's evaluated at p, and exactly same game that we are playing here. So gamma prime x gamma prime 0 g alpha beta comma gamma prime, and again evaluated at p plus half I need to write the derivative of g. So this is the second derivative evaluated at p plus higher orders again. Right, so this is g alpha beta. Now this is known. This is a metric which is already defined in the manifold. So this is something which is known. It's not that we can change the different terms of g. This is already known. You are just writing it in terms of uh, some other point. But what is not known, what we are supposed to fix, is the lambdas, uh, is the coordinate transformations. So let's look at those. So let me make the comment that we do not know what are lambdas. We need to fix them. Right? So that is what you want. Now, lambda alpha beta prime, we do not know, but we can expand them also exactly the same way about the point P. So let me see. We called it lambda alpha mu prime. So let us do that here also. So alpha mu prime and alpha mu prime. So lambda alpha mu prime evaluated at P, and then plus again this 0 is just the reminder that that is the point where, that's the point P. It's not any index as such. And then lambda alpha mu prime. So I have to have a partial derivative of lambda alpha mu prime with respect to x gamma prime. But lambda alpha mu prime itself is del x alpha del x mu prime. So I get this. And if I write the next term, let me write the next term. This has to be evaluated at P, lambda prime minus x naught lambda prime. And you can imagine that I will have three derivative now. Okay, I have can write lambda beta nu prime also just the same way, but I know that you are quite good to write that down, so I will not write it explicitly. What we will do now is that I have the left hand side here for the 0th order. I'll collect from the right hand side terms of the 0th order. 0th order in x minus x naught essentially. So let's do that. This was to be evaluated at P also. Okay. So the left hand side, the first term was G mu prime evaluated at P. In the right hand side, that term will come from lambda alpha mu prime evaluated at P. Similarly, lambda beta nu prime evaluated at P, and G alpha beta evaluated at P. Okay, so let's ask the question now. This is what? So we want this of our choice. So we want this to be of our choice, and the choice happens to be eta mu prime nu prime. So that is what we want the metric to be locally, right? If I want to fix this, need to fix how many components we need to fix for this when I say that G mu prime nu prime has to be of my choice. Well, G mu prime is symmetric. It's a four second rank tensor, second rank symmetric tensor. So I need to fix 10 components here, right? A second rank symmetric tensor has 10 components. So I need to fix 10 components. Now, to do that, what do I have in my hand? We have choice for lambda alpha mu prime. How many components does it have? Well, this is a coordinate transformation. There is no need it has to be symmetric. So this has 16 components. I'm sorry, this is not a coordinate transformation. It's a transformation from x prime to x. It's not a coordinate transformation in the sense of Cartesian to polar type, but it has 16 components. So, which means that we can choose, we have essentially 6 extra choices, which is basically saying that I can choose lambda, the 16 components of the lambda in such a way that 10 of them I can just fix to match with G, but then there are other 6 choices which are left, and those 6 choices you can do whatever it is, you will still get eta locally for the G. So that is possible to do using, because I have 6 extra components. Now this turns out to be, so I have certain choice. Even when I fix those 10 components, these 6 components have certain choice, and these choices are turns out to be the 3 space rotation. So these are 3 of them, and 3 space time rotations, so which are essentially Lorentz transformations. So this is 3, that is 3, total 6. So that 6 and plus 10 choices to keep the metric locally as eta mu nu. So that exhausts all the choices of lambda alpha mu prime. So if I want to find a metric which is locally Minkowskian, I can do it. But wait a second. Maybe I have fixed the 0th order, but that is not good enough. I should also make sure that the first order terms, which involves the derivatives of del lambda and delta g, they there should not be any choice in there because they are all supposed to be 0. The derivative of g in the local inertial coordinate with respect to the coordinate should vanish. That was one of our requirement. So let's ask the question if that is true. For that, I have to go to the first order. So this is the 0th order. So let's come to the first order. So when I say first order, again it is in x minus x prime. Now how does the first order terms look? Well, to get a first order term, let us look at the g and lambda. So remember that I have two lambdas and one g. Now to get a first order term, if I have the first order term in g, I have to two first order terms in lambda. And if I have one first order term in lambda, then the other lambda has to be of 0th order, which is this term, and the g also has to be of 0th order. Okay, that is how you can make the coefficients. Basically, what you are doing is you are collecting the coefficients of x minus x naught. Okay, so let me write down the first order term. You can verify. This will be del g alpha beta, and gamma is the coordinate with respect to which I am taking the derivatives. So this is evaluated at p. Then lambda alpha mu prime. So lambdas, because I have taken the derivatives of alpha already, g already, I cannot take derivatives of lambda. Then I will get a second order term. This plus, now I can keep g fixed happily and take a derivative of lambda. So that is del 2x alpha del x prime gamma del mu prime, and the other has to be kept fixed. All of these are evaluated at p, so I'll write that together here. And again, g alpha beta. Now what do you want? You want the left hand side, if you remember, for this is essentially 0. So you want this entire thing should be 0 for all values of mu and nu. Okay, so let's ask the question that how can I do that? Remember that g we don't have any choice for. The only thing we have choice for is, right now the only thing we have choice for are these quantities, because the choices of lambda we have already exhausted. The lambda at the given point p we have already fixed to fix the first order term to beta, that we have already fixed. So now the derivative of the lambda, that we can still fix. And what is the left hand side term? So that is, it is important to write that down. The left hand side term is mu prime nu prime and say del x gamma prime. You may be wondering on that where that gamma prime comes from, but that is because you have a x minus x gamma prime minus x gamma prime not squared multiplying both the left hand and the right hand side terms. Fine. Let's ask the question, how many components do I have? So how many components we need to fix? Well, again, G is a symmetric second rank tensor, so it has 10 components. And each of these components can have derivative with respect to x. and there are 4 x's, so there are total 40 components. So the components we need to fix here are 40. So I have to fix 40 numbers to be 0. How many components can we fix? How many can we fix? We have 40 components to fix, but then out of those 40, how many do we have a choice to fix? Well, you see, this quantity is all that we can fix. Now, I'm taking a second order derivative with respect to 2x's, and that second order derivative itself I can swap between. I can put the x gamma prime first and then x mu prime, and either way. So that's a symmetric object. It's a second rank symmetric object which again has 10 components. And now I'm taking the derivative with respect to these 10 differential operators of 4 things which are x alpha. So again, I have 10 into 4 equals 40 components. So I can fix 40 components. I can manipulate 40 components to fix 40 components, which is a perfect choice. So it's a perfect match. So I can do it unambiguously. So this is telling you that I can fix the first derivative of lambda. I can choose the 40 values for the first derivative of lambda such that my derivative of the metric tensor with respect to the local coordinate system is 0. Okay. So this is telling you that I can find always a coordinate transformation where the 0th order, the metric becomes eta, and the first order, which is the first derivative of the matrix, is always 0. Now what I will not do for you and leave it for you as an exercise is the following, that check that second order onwards, and let me keep a question mark where you should think what is the second order actually. We cannot fix transformation such that the local higher derivatives of the metric, we have vanished the first derivative, but local higher derivatives vanish. We cannot do that. So cannot is important. You don't think that we can do it. We cannot do it in an arbitrary manifold, which essentially tells you that this local higher derivatives of higher order carries the information about the property of the manifold. So this carries the information about the property of the manifold. And this property is essentially the geometry. So let me write geometry of the manifold. So that proves that we can figure out a coordinate, should not say coordinate transformation, but a transformation which brings an arbitrary manifold, arbitrary metric in a differentiable manifold to a local Minkowskian form. And that is essentially telling you that this business of manifold is a very good business to explain the general relativity, the mathematics of general relativity. Okay, so let's look at uh, two things about the manifold or related to the metric. The first question is that how do I calculate the volume in such a manifold? So, volume calculation. Okay. Or I mean, you can think of that. How do I write the arbitrarily small volume in such a manifold? So that will be just essentially the volume integration you can do if I know what is the differential volume. So if I write the differential volume as dV, this I can easily write as dx0, dx1, dx2, dx3. This is in Minkowskian system, right? Now you know that I can also write it in terms of any arbitrary system. Let's call them dx0 prime. So this is arbitrary now. dx1 prime, dx2 prime, dx3 prime. But then I have to multiply it by the Jacobian of the transformation. And the Jacobian of the transformation, we have already shown that such a transformation exists. And now I can ask the question, what is the Jacobian of such a transformation? It is this is the following determinant. It's the determinant of del x0, del x0 prime, etc., etc., which is essentially, I didn't write it because it is simply determinant of the transformation matrix. Okay, now we have to calculate the determinant of this matrix, and it's easy to figure out the determinant using a trick. This is what we need to calculate. Why we need to calculate this? Because if we can uh, calculate this, if we know what it is, then I can figure out what is the volume element or the differential volume, because this is the it's called the measure of an arbitrary system coordinates. So I just multiply it or I put the Jacobian function before that, and that will give me the differential volume. Okay, so how do I calculate this? Well, I remember that G alpha beta, which is the metric in the arbitrary system, is given by okay. Now, because all of these are just second rank objects, the metric and eta are second rank objects, and the transformations are matrix, we remember that we can write such second rank objects in terms of matrices. And we know that if I take determinant of this expression, I get determinant of G here equals 2 into determinant of lambda, which is essentially determinant of lambda square, and then determinant of eta. Now, determinant of eta is the easiest thing to calculate in the world, that is -1. So, which tells me the determinant of lambda is square root of minus g, where I write g for the determinant of the metric. Okay, so what do I get? Volume element in arbitrary system, arbitrary coordinates, is dv is square root of the determinant of the metric in that coordinate times the measure. So let us write them again as 0 prime. It's customary to put this in a test in, say, 2D polar system. 2D polar case, remember that we calculated g. This was 1, 0, 0 r square. So dv will be root over of g times the determinant of the unit matrix, which is 1. So it is root over of g in this case, not minus g, and then dr d phi. And root over of gr is g is r here. So r dr d phi, which is exactly what you expect the volume element to be in the 2D polar case. I request you to calculate the volume element in this way just by using the metric in that given whatever system that you think about. Okay. So now that we have figured out that the differentiable metric manifold works as the manifold for general relativity, let us go ahead and try to figure out or try to argue against how should a particle move in presence of in general relativity, essentially. Okay, in presence of gravity, so to say. I have not bring in gravity yet, but we said in presence of gravity we need to work in this such manifolds. So in such manifolds, how will a free particle move? Okay, so let's ask that question. How does a free particle moves? Okay, so now this question we have answered earlier in case of the inertial frame, and we said that for a free particle, the proper time spent to go between two events is maximum for the curve same as its trajectory. What do I mean? I mean that if I want to draw a space-time diagram here with, say, again one space axis, this time x only, and we say that there is one point here where the particle was, this is the event, one event, and this is another event, and in this particular coordinate system, maybe this is one way I can join the events A and B, and there are many such different paths between A and B. But this, our discussion earlier told us that for the correct trajectory, the proper times spent between the two events is maximum. Or you can consider anything multiplied by the proper time, and that will be an extremum. Now, we showed that considering the reference frame of the particle itself, where the particle is obviously at rest, but we said that because it's a proper time, the proper time doesn't change. Proper time spent between two events doesn't change as you change the reference system. This should be true. This statement that we have written down here in the left hand side should be true for any reference frame. This is actually true even if you go from a local inertial frame, from an inertial frame to elevate this to local inertial frame. So still the proper time spent between 2 points will be the extremum for the particle trajectory. How do I say so? Well, you can break up the trajectory of the particle between A to B in many small segments. And as the particle moves, you can have an observer who is freely falling for the particle, which means that is essentially having the same property as that of the particle. It's not an observer quite at the particle, but very nearby. For that observer, the particle will appear to move in straight line, because for that observer, the particle is in a local frame, and that local frame is, by our definition, inertial. And in that inertial reference frame, it is supposed to move in a straight line. It's supposed to follow this property. And now if you add up these small segments, which you divided the path into earlier, then the statement will still be true. But things will certainly change about the equation for the trajectory. So that's what you will see now. So remember, you wrote down the Lagrangian earlier for such a free particle. It's essentially root over of g alpha beta let us say for the time being. Okay, so one way of parameterizing the path of the particle is by the proper time, and that is what we will do right now. But there are certain caveats. One like to use a different parameters, at least for certain type of trajectories, but I will not bring that in, at least today. So I write the Lagrangian exactly like this. Okay, so this is the Lagrangian. What I have to do is to find out the Euler-Lagrange equation. Remember that this I can also write as root over of g alpha beta u alpha u beta. So what is del L del u mu say? This we have calculated earlier, and this will be simply g mu beta u beta divided by this entire thing, but now I can write this as, so that's essentially C. On the other hand, so this we did earlier also, but if I calculate now this quantity which was 0 earlier, it will not be 0 anymore, because g alpha beta now depends on the coordinates. So this will again be, this will denominator will be still C, but in the numerator I will have g alpha beta comma mu. So I have to take a derivative of g alpha beta with respect to mu, and I will have a half because I had a root over there. Okay, so this is the left hand side is also the canonical momentum. And now the Euler Lagrange equation, to calculate the Euler Lagrange, to get the Euler Lagrange equation, I have to do a dd tau of, so let's take the 1 by c outside. I have to do dd tau of this. And now when I do this, you see, earlier I just could have just write down this quantity du beta d tau. But now remember that g is a function of all the coordinates, and I'm taking a total derivative, which means that those coordinates, as they implicitly depends on tau, I have to take that into consideration. So this will be u beta, and now I have to take a derivative of g this with respect to tau, but that I can write as, say, alpha and then u alpha. So I want to take the derivative of g mu beta with respect to tau. That's a total derivative. But that total derivative, by chain rule, I can write a partial derivative with respect to alpha, and then I need dx alpha d tau, which is essentially u alpha. So if I equate now this with that, I get the Euler Lagrange equation. So let us write that down. So I get g mu beta, 1 by c cancels out, so it's not of much importance. This plus u beta u alpha g mu beta comma alpha, and del L del x mu comes with a minus sign. So this is half g alpha beta mu u alpha u beta. And Euler Lagrange equation, so this is equals to 0. Work out a little bit further. So this is g mu beta du beta d tau plus, you see, both beta and alpha are dummy indices, which means I can write this u alpha beta if I take common outside. The first term I can write as the sum of g of mu alpha comma beta and g of mu beta comma alpha. But if I add them two, so I have half, I have to take a half outside, and the third term already have a half. So let me write it this way, this entire thing times half. So I do a trick now where I multiply from the left with something like nu g nu beta, nu mu, sorry. Let's see what happens if I do that. The second term is interesting because this is half g nu mu and then g mu alpha beta plus g mu beta alpha minus g alpha beta mu, and this entire thing is 0, of course. This term is just a delta, and when I do the sum over beta, the beta in the left hand side, beta in the u, will become a nu. So this is essentially g d u nu d tau plus, then what is this entire quantity? And I forgot to write the u alpha u beta here. But apart from that, what is this entire business of half g and g's is essentially the gamma. And this is gamma nu alpha beta u alpha u beta, which is equals to 0. So this is the equation for the shortest or the longest or the stationary proper time. So if you consider the space-time language, this is the shortest distance I can keep in. So space-time distance between two events. This is an equation for. This is not quite the algebraic equation, it's a differential equation. But once you solve it for the proper initial conditions, you will get the shortest distance between the two events. So this equation is called the geodesic equation. Shortest distance between 2 points is called the geodesic. Shortest distance between 2 points is a straight line, which is what is the definition of a straight line. The straight lines in more general form is called geodesics. So what is that a particle will do which is not exerted by any external forces? And when I say any external forces, obviously I exclude gravity, because remember the strong principle of equivalence told you that if you are in the local inertial frame, then the equations of motions will be that of an inertial frame. Now what we are doing is, the local inertial frame is valid only at a given point or near to that point. We are going from one point to the other point or one event to the other event, which are quite far away. And we are saying that there is no other external forces. So there can be forces of gravity, but that force is now changed to a manifold, which you'll see how it is done. But what will essentially we see now is that effect, which will be there in this quantity, is called gamma. Actually, the derivatives of those, because see, gamma is the first derivative of g, which are locally 0, but the second derivative of gamma will give you the properties of the manifold or the curvature of the manifold. First derivative of gamma and the second derivative of g will give you the property of the curvature of the manifold. And this equation tells you how a free particle will move in such a manifold. Okay, we'll discuss a lot more about this equation in the next class. But I will leave it for you here today. Today we have shown how we can choose a transformation always in a metric differentiable metric manifold, such that from an arbitrary g we get a local Minkowskian g, which is eta, which has first derivative 0 at that local neighborhood. Second derivative we cannot control, second and higher order derivatives we cannot control. We also have seen that if in such a manifold there is a free particle moving from one point A to another point B, what is the differential equation that will decide the trajectory of that particle? Thank you.